on a little bit. So, what we had discussed was the idea that we can produce entangled states of light through nonlinear optics. And in particular, the most important processes we can think about as happening in three-wave mixing, where we have some kind of strong pump, as we had discussed before, and so I have some kind of strong pump. Let's see, is this thing? Let me make sure hold on a second. I'm gonna do this and bring it back up and see if I have the pen is connected. There we go. All right. Right. So what I was saying is we have this strong pump and pumping on this Chi2 crystal. And we discussed this in the context of parametric amplification, where we could amplify a signal and we would get this kind of also conjugate beam. But importantly, if we don't include this, if that is not injected, then we have the process of what's called spontaneous parametric down conversion. And spontaneous parametric down conversion is the situation where you just pump the crystal, and then you'll generate spontaneously conjugate pairs of beams, the signal and idler beams, such that they satisfy the phase matching conditions. But because there are multiple ways that you can satisfy the phase matching condition when you don't inject the signal, then what you really have is a superposition of all the different ways that you can satisfy that phase matching condition, which correspond to different directions and different colors of the photons, okay? Moreover, what we have in this situation is that the polarization of the light that is coming out depends on the nature of the crystal and the nature of the phase matching conditions. In so-called type 1 phase matching that we have, then everything is in the same, the signal and either have the same polarization, okay? So the phase matching conditions then determine the color and the direction of the photon, but its polarization is fixed. So the kind of entanglement that we see in this kind of process has to do with entanglement associated with the motion of the photons, okay? And that is to say, their motion along their direction of propagation and the motion sort of perpendicular to the main direction of propagation. And that was sort of the first kind of phase matching that was done for making entangled photons, was based on this type 1 phase matching, okay? And so we end up getting this kind of situation. If we were to do this with a strong beam, we'd end up with what is called parametric fluorescence, where you pump the beam and you get this fluorescence of light coming out in cones. The cones, things that are on a definite cone, have a definite color, okay? And there's then a spectrum. Now, actually, I just noticed that this is backwards. The longer wavelength should be in the middle, and the higher wavelength should be, the green should be on the outside and the red should be on the inside. I have to fix that, but oh well. This was never noticed before. But importantly, what we have is this idea that we have these conjugate pairs of beams, and they're denoted here with things of the same shape. Okay, so I could have a conjugate set of photons there, a red and a green one, that together would add up together to the pump. Okay, and they come out on these cones, they come out in those directions. So if I were to put a pinhole as I kind of drew, I would get, a signal and an idler photon coming out in a conjugate pair. Or if I put a pinhole here, I would see a conjugate photon there, because those two directions of propagation satisfy the phase matching conditions. Or if I put a pinhole here, in this case, I'd get a degenerate one. That's to say they would have the same color, but it would come out in a different direction. Okay. Now, it's not the color that comes out is actually spread depending on the size of the pinhole. Okay. So I'd have a spectrum of colors across there. Okay. And that led to the whole idea of what was called time energy entanglement. The time energy entanglement has to do with the fact that there is a correlation associated with the movement of the photons along the direction of propagation. It's a kind of wave packet. And the entanglement is such that two photons that come out here in these pairs have a kind, because of the phase matching condition, are correlated in some way in terms of their center of mass motion and their relative motion. And what that looks like is this kind of two-photon wave function. Okay, so the two-photon wave function is associated with this spontaneous parametric down conversion, such that the two-photon wave function, ideally for perfect phase matching, would look like this. Okay, that is to say, the two photons have each of the photons, the signal and the idler, have a wave vector whose sum adds up to the wave vector of the pump, and whose length or frequency adds up, with the color being the same. And that wave function I can think about as one in which along the direction of propagation of the photons, their center of mass is well defined, but their relative position is well defined, but their center of mass is completely undefined. And what that means is that and that's kind of shown here in the following idea. So the idea is that I have these two pinholes over here, and those pinholes take a spectrum of photons that's relatively broad, such that I can think about it as basically a flat spectrum. It's broad enough that each photon has a very broad bandwidth, which means each photon is a very short pulse in time wave packet, because its spectrum is very broad because the pinhole is sufficiently big. However, the relative frequency is very narrow because of its entanglement. They have to, all the difference in the frequencies have to add up to the pump. Okay. And so what that means is that the two photons are born nearly at the same time. Okay. But we don't know when they were born. Their center of mass of the two photons is undefined, but there are, if one is born, we know the other one's there. Okay. And that is what's sometimes known as time energy entanglement. Why time energy? Well, it's because the, you know, the color of the photons is completely undetermined. We don't know what this big pinhole, but the time is the relative time is very fixed. Okay. And the first experiments that were done that showed that were done in what was called a Franzen interferometer. So Jim Franzen proposed this idea sometime, oh, I don't know, around 1990. And the idea was that you would look for two photon interference. Okay. So two photon interference means that the interference is seen in the coincidence counts that one sees between two photons. The interference is between the possible histories that the two photons could have lived through to get to the final outcome. If there are different histories that lead to the same outcome, and those two histories are in principle indistinguishable because there's no information anywhere that tells you which of those histories happened, then what Feynman taught us is that we need to sum the probability amplitudes for those processes and then square to get the probability of the outcome. Okay. So the outcome is two photons are detected at the same time within some narrow window. And there are two ways that that can happen. Now, one thing to note is that there's no one photon interference here if these individuals, so what we have here are two Mach-Zehnder interferometers in these two arms of this interferometer, this two photon interferometer, and they are unbalanced. Okay. And what that means is that the coherence length of an individual photon going through this interferometer is short compared to the difference in the path lengths that I'm calling here short and long. Okay, which would mean that if a single photon went into one of these interferometers, if it went through the short path, it would come out very quickly. If it went through the long path, it would be fairly delayed. And if that delay time is longer than the extent of the wave packet in time, then these two wave packets are distinguishable. They won't overlap and there will be no interference. So if I were to look at the probability of seeing a photon at the output of one of these ports, it would show no dependence on the difference as long as it was unbalanced. I would see a rate of counts of individual photons that would be independent of the path length difference. Okay. On the other hand, if I look at the um, two photon histories, there are two different histories that can lead to the same outcome. That is to say, both photons arriving at the same time. One is they both went through the short path, and the other is they both go through the long path. And of course, they would require different birthdays for those to happen, both of those to happen, to be the same final outcome. But we don't know when their birthday was, and so there we have coherence between different birthdays of these twins. And as we discussed, so what we do, we just add the probability amplitudes associated with these two processes. Either the signal can either go through the short path or the signal can either go through the long path. And 1 and 2 represents the upper arm or the lower arm. And when you do a little bit of manipulation, as we discussed, this gives us a coincidence rate that oscillates at the sum frequency, the frequency of the pump, even though what we're measuring are the down-converted photons at low frequency, the signal-Neidler. What we'll see is a two-photon interference pattern that oscillates at the frequency of the pump. And that experiment was done in the lab of Ray Chow with Paul Kwiat and Ephraim Steinberg when they were PhD students, and we were all in the same group at the same time. And what's shown in here is some data taken from this paper from Physical Review A in 1993, which shows the singles counts as a function of the path length difference, which is flat, shows no interference, but we see two-photon interference that way. Okay. Let me pause for a moment to see if there are any questions. So this is a kind of this entanglement is entanglement associated with the spatial position of the photon relative to its main propagation direction. There's also an entanglement associated with the transverse mode. I'm not going to talk about that. It's kind of more complicated and not really that interesting, in my opinion, although it could be used as another degree of freedom in which to encode correlations. These are both the motion along the direction of propagation and transverse are continuous variables. They represent infinite dimensional systems. And so in principle, you can have entanglement with many entanglement bits. It's not just a qubit that's being entangled in these things. Okay. Right. So let me turn my attention now to the idea of making entanglement between the polarization states of two photons, okay? That's interesting and useful when we want to think about things like Bell's inequalities and the kind of EPR experiment, but not done with continuous variables, which, as we know, unless we have non-Gaussian states, it's very complicated to think about Bell's inequalities. It's much easier to think about them and prove them for qubits, okay? So what we want is for the photons to come out with different possible polarization states. what we discussed a moment ago is that if I have type 1 phase matching, they have the same polarization, so there's no entanglement between the polarization state. However, if we use so-called type 2 phase matching, then the signal in idler can have orthogonal polarizations. And that has to do with the fact that the crystal is strained and has one axis where the polarization, the index of fraction is different from the other. Okay, so that's called birefringence in optics, and there is a fast and slow axis. One of the indices of fraction is higher than the other. And by playing around with the phase matching conditions and the axis of the stress and strain relative to the axis of propagation doing the magic of optics, you can make it such that you have phase matching for these two orthogonal polarizations that are called horizontal and vertical. Okay. And the phase matching conditions are such that the signal in idler fluorescence, that's to say the horizontal and vertical polarizations that come out, are not along the same cones. So we have this separation of these cones, okay? But importantly, right here, we have a situation where the two cones coincide. Now, let me emphasize a fact before I get into that. If I might have a phase matching condition where, say, this is phase matched with that. Okay, so I have a red photon propagating in that direction that is horizontally polarized, and a purple photon propagating in the other conjugate direction, which is vertically polarized. In that situation, would I see entanglement between horizontal and vertical? The answer is no. Why not?
You can tell by the color, right?
That's right. They're distinguished by their wave vector, their length and direction. So if I'm only measuring the polarization, I'd have to trace out the other degree of freedom, and I would lose. They're distinguished by them. I have to have, in order for me to see entanglement between these degrees of freedom, that degree of freedom can't be correlated with any other degree of freedom. Because if it's correlated with the other degree of freedom, it's entangled with that other degree of freedom. And once I trace out that other degree of freedom, I lose the entanglement. It's sometimes called the monogamy of entanglement. You just can't be entangled with more than one degree of freedom at once, I don't know if there'll ever be a revolution, a monogamy of entanglement revolution, but for now, that's the law. And so in order to see this, we have this one special case where there are, for that green photon and that direction, I can't tell whether it's horizontal or vertical. Okay. And so in this, if I put pinholes there, those photons would look like the following. What I would have is a situation where I can factor out the directions, okay? So if I look at this situation where I have one photon in the signal and one photon in the idler, or vice versa, okay? Because those two pinholes overlapped, okay? So this is the second quantized form of that picture. Okay. That's to say, K1 is one pinhole, K2 is the other pinhole. And I don't know whether that pinhole was on the horizontal or the vertical. So I have a superposition of the two with some phase between them that depends on the nature of the crystal. Then if I look at that in first quantized form, because the horizontal and vertical are distinguished by their wave vector, each one of these guys I don't have to symmetrize. It just looks like this, and this looks like that. And what that means is I can factor out the motion degree of freedom from that. It's not entangled with the spin degree of freedom or the polarization. And that's a two-photon entangled state. That's entangled in polarization. It's not entangled in this case in the the K1 and K2 if I have a very narrow pinhole. Of course, if I had a wider pinhole, I can factor out, I can have both entangled. I'll come back to that, as I don't want to get confusing. Okay. Now, one of the things that was a challenge for that is that you're really throwing away most of your photons because you have this pinhole and all the other ones that come in the other colors and so forth, uh, you're throwing them away. And Paul Kwiat had this idea that if we can somehow make these two cones, the horizontally polarized cone and the vertically polarized cone, spatially overlap everywhere, then we can have a large number of directions of propagation of photons, all of which I factor out the spatial degree of freedom. I make it indistinguishable what direction the photon was propagating in, because in every direction, there's both an H and a V way it could have been born. And his idea was to have two type 1 crystals, one that emits only horizontal and the other one that only emits vertical. Okay. But we have to have it such that we can't tell which pump did it. The pump should be in a superposition of maybe the pump down converted into horizontally polarized photons, or maybe the pump down converted into vertically polarized photons. But the deal is that in type 1 phase matching, the pump is polarized perpendicular to the down converted photons. But if you put the pump at 45 degrees, then there's a chance the pump was polarized like this, in which case it could emit this kind of photon, or the pump was polarized like this, in which case it emitted this kind of photon. And if you make the crystal short enough, but still long enough for phase matching, then you can't tell where the photon was born, and you overlap these two. And this kind of source makes a very powerful source of entangled photons. In fact, it's so-called hyper-entangled in that it can be simultaneously entangled in polarization, the temporal mode, time and frequency, and the spatial mode, transverse. All of those degrees of freedom are entangled. That's a sort of a icing on the cake. It's really this part, the the polarization entanglement that was used to really show the best. I guess, am I showing it here? Hold on. Yeah. But anyway, I don't have that on this, but the best um, violations of Bell's inequalities and the eventual loophole-free EPR experiments that were done with this kind of source because you get and this source was developed in Antoine Zeilinger's lab. Paul was Antoine's postdoc. And that's part of what led to Antoine winning the Nobel Prize in physics. Anybody have any questions? All right, I will continue. But wait, there's still more. Um, so one of the ways we let off our discussion regarding entanglement uh, in the electromagnetic field is there's lots of different kinds of degrees of freedom we can think about. In particular, if we think about this as a bunch of particles, we can think about the entanglement between the degrees of freedom of the particle, their motion and their spin. That's what I just talked about. The motion could be along this direction, along that direction. And there's the spin degree of freedom, which is the polarization of the photon. And we thought about two particle entanglement between the different degrees of freedom of two particles. We can also think about, those are kind of discrete variable description of the quantized field. But as we also discussed, we can think about the collective wave-like degrees of freedom of the field, where we think about the oscillator, the quadratures, the X and P quadratures, which are simple harmonic oscillator-like degrees of freedom, or the modes, and think about entanglement between the different modes. Each mode is like a degree of freedom of the field. Okay. And mode entanglement is really interesting, really useful, and may be the basis of the quantum computer of the future. We heard a very interesting talk, uh, um, a number of them here at the APS March meeting regarding so-called dual-rail encoding of a qubit in either one mode or a 0 or 1 has to do whether it's in one mode or the other. And that could be the best way to make a superconducting mode qubit. So anyway, you never know. So what am I talking about? So what we just talked about was parametric down conversion. And the parametric down conversion was this three-wave mixing process. And we looked at, maybe I should go back. I have to see. Let me see if I can find. Hmm. I'll just write this. I'll just write this down. Uh, right. So, when we had our, our Hamiltonian involved, some kind of possible weighted sum associated with creation of signal and idler photons with some weighting here, and then we have the conjugate. This was kind of our three-wave mixing Hamiltonian, right? Where we treated the pump classically, and we have the situation. By the way, is this screen, is this in your, do you see are you seeing the full screen? You're not seeing the everyone's camera blocking the screen in any way. Is it okay for you?
No, no, we don't see other people's
Okay,
camera.
good. All right. Um, of course, what you see is not the same as what I see. Um, and loosely, if I think about the evolution of the system as, okay, this is the parametric down conversion happens like this. And we said, for low orders, that's like the vacuum, and then, the two photon sector of this, and the two photon sector of this has to do with, all the different ways I can create signal and idler photons acting on the vacuum, plus dot, 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 right? And what we did is we said, oh, we're going to just post-select by looking at coincidence counts where we see two photons. Now, of course, there is a 4-photon sector in it, but it's typically, these are weak processes, and to dominant order, it's dominated by it's basically a superposition of the vacuum and two photons, okay? But we threw away the vacuum component of it. We just post-selected on the two photon component. Now, particularly when these guys are degenerate, we remember that this unitary is the same thing as the squeezing operator, right? And what we have seen is that the the squeezing, if I were to look at that, I took it for this because I noticed this is for the particular case of a squeezing parameter being negative R. So this is that squeezing parameter and that squeezing operator. That squeezing operator is a superposition of all the even numbers of photons, right? It has some zero, no photons, it has a vacuum, it has a 2-photon component, a 4-photon component. That's what we expect from parametric driving, which is intimately related to squeezing, which gives, so from the continuous variable point of view, we're shaking the oscillator at twice its frequency and seeing a parametric resonance. From the point of view of the quanta, we can have 0, 1, 2 photons when we're driving it at twice the natural frequency, okay? And the actual expression, which I don't think we ever wrote down for the decomposition of squeezed vacuum into Fock states, has this form, okay? So that is to say there's a certain probability amplitude in each of the sectors, for each Fock state that's written over here. It's a superposition of 0, 2, etc. And that coherence between the vacuum and the 2-photon sector gives you squeezing. In this case, I've squeezed the P quadrature and anti-squeezed the X, okay? So this parametric fluorescence process, the optical parametric amplifier also gives me squeezing. Now, importantly, if I don't, if my squeezing is such that my parametric amplifier uh, is phase matched, not for the degenerate case, but for two different modes, then I have what we call two-mode squeezing. Okay? So the two-mode squeezing is here. And that corresponds to a signal and idler that are not degenerate. Okay? And I could, in principle, I would get that for free in parametric fluorescence, but I could also make a special cavity, maybe, that is specially resonant for these two modes. But let's just discuss it mathematically. Now, this is something you studied a little bit in your uh, homework, right? Maybe more than a little bit. And um, if we use this, a little bit of math tricks, what we find is that the two-mode squeeze state, two-mode squeeze vacuum, has this form. Okay. So it's a generalization of what we saw for the single mode squeeze state, where we have superposition of Fock states, where A and B represent the two different modes, the signal mode and the idler mode, which are not the same. Okay. They could be different colors. They could be different directions. They could be different polarizations, whatever it is that distinguishes those two modes. Okay. Now, just off the top, just looking at this, is this state entangled between the two modes? It is. In fact, this already is the Schmidt decomposition. For the two-mode squeezing, the Schmidt vectors are the number states. And these coefficients are the Schmidt coefficients. Interesting. So this state is entangled. It's entangled between the modes where the Schmidt vectors are the Fock states, such that we have what are called twin beams. That is to say, if I count n photons in mode A, I'm guaranteed to see n photons in mode B. They are twin in terms of the number of photons I see in each of these modes. There's no number fluctuation in the relative photon number between the two beams. Okay? That's because they're born in this pair-like process together. Um, okay. Now, so this is what I just said. These are the Schmidt coefficients, which means that if I were to look at the marginals, so if I were to look at one of the beams without correlating it with the other, that mode or that beam of light will not be a pure state. It will be a mixed state. And the degree of mixing will be inverse will depend on the amount of squeezing or the amount of correlation. The more entangled the two beams are, the more mixed the marginal is, because the joint state is pure. And what is that mixed state? Well, it's a statistical mixture of Fock states with the probability given by the square of the Schmidt coefficient. Right? Everyone with me? At least somebody. And here they are. And if we look at this problem, what we see is this has the form of a thermal state. That is to say, this is the Bose-Einstein distribution. Where the mean number of photons we did calculate for a squeeze state is the sinh, the hyperbolic sine squared of the squeezing parameter. Okay. And what we see here, this should be to the power n, is what's sometimes known as the thermofield double. If I have a Gibbs-like state, which is where P sub n is a Boltzmann distribution, I can think about this as the marginal of that. So this is, I've doubled the Hilbert space and made this pure state such that the marginal state is the Gibbs state. That's sometimes known as the thermofield double. And that's what comes out of the squeezed two-mode squeeze state. A two-mode squeeze state is like a thermofield double. The individual modes are thermal photons, but the correlation is perfect. Interesting. There's lots to unpack there. So
I even have a question.
I'm listening.
This cannot be true for every entangled state in the number of photons, right? This is just specifically squeezing.
That's right. It's not for every kind of entangled
Yeah,
state,
yeah, yeah.
but it's
So
true
squeezing
for
has this property.
the squeezing has this property. Yep. You know, and the amount of entanglement you get grows like, so if in the limit that the squeezing parameter goes to infinity, the tangent, you know, what happens is I have an equal superposition of all possible pairs in this case. And in that, so I can have, you know, if I go back to this expression for the two-mode squeeze state, in the limit that the squeezing parameter goes to infinity, this becomes flat, and I have an equal superposition of either I have nothing or one photon or two photon, and the marginal is the infinite temperature Gibbs state. Okay. That's in the limit of infinite squeezing.
Is that in some sense the maximally entangled state?
It is. You'd have infinite bits of entanglement,
Interesting.
right? It's a qubit with an infinite dimension, and it's the most entanglement you could possibly get
I see.
between in a bipartite system.
Right.
Okay, so this is Victor. I have a question. So can you realize infinite squeezing?
No,
Okay, so
absolutely not.
it's a limit, yeah.
It's a limit. But
Okay.
the more you get, the better you get. But
Yeah.
of course, you cannot get infinite squeezing. That would take infinite energy. In just even in principle, it's not a practical consideration. In principle, there's just no way to have infinite amount of energy.
Yeah. Okay.
But it's kind of like the limit of a position eigenstate. There's no such thing as a position eigenstate because I'd have to have it infinitely localized. It would have infinite uncertainty and momentum, and that's impossible. But I can get as close as I can. Well, I can try to get closer.
Okay, thank you.
Yeah. So let's talk about that a little bit more. So I described this two-mode squeeze state in terms of its entanglement between the number of photons. But I led off my discussion talking about the quadratures. So I can think about the quadrature degrees of freedom of the two modes, the x and p associated with mode A, and the x and p associated with mode B, where x and p now are the quadratures. They're not the position and momentum of the photon. They're about the quadratures of the oscillator. Okay? Now, first thing to note, if I ask you the following question, what is the Wigner function of the marginal? So the reduced density operator, also known as the marginal density operator, is a thermal state. What is the Wigner function of a thermal state? Anyone remember? It's a Gaussian.
Yeah.
Right? It's a Gaussian with a width that depends on temperature or the mean number of photons, right? At zero temperature, it's the vacuum, and then it gets to be a wider Gaussian. So, the marginal is Gaussian. What about the joint? So let's think about this from the point of view of the two modes. I have a joint Wigner function for the two modes. I'm calling alpha and beta the complex amplitudes of the two modes, mode A and mode B. So, here's an expression based on take the characteristic function and then inverse Fourier transform it. The characteristic function of the two-mode squeeze state is a Gaussian. And thus its inverse Fourier transform is a Gaussian. And here it is. And if I were to rewrite these in terms of the real variables, x and p, then it turns out that this is the two-mode Wigner function. Mode A and mode B. Mode A has an x and p, and mode B has an x and p. Notice the form of this. It happens to factorize in terms of the position space wave function of the two modes, which we can write down, right? I can write the position space representation of the two modes because the x is commute and the momentum space wave function. And this is a plot of the marginal state associated with the position and the marginal state of the momentum. And what we see in two-mode squeezing, and this is what's important, or one of the things that's important, in two-mode squeezing is what's squeezed beyond the relative number fluctuations is the relative quadratures. Okay, so for the particular choice of the, it could be either way. What we see here is that the relative x is squeezed, whereas here the center of mass momentum is squeezed, and the vice versa. Therefore, the relative momentum is anti-squeezed, and the center of mass position is anti-squeezed. In the limit of infinite squeezing, I would have something that was a delta function in the relative x and completely uncertain in its center of mass. This is not mass, this is quadrature, and vice versa. This is just the EPR state yet again, but now in quadratures. And this was, used in various other experiments of looking at EPR. But, interestingly, the Wigner function here is positive everywhere and Gaussian everywhere. So these correlations are correlations we could create with classical oscillators just by, rolling the dice and setting the relative coordinates and momenta in the right way, and you did measurements on them, it would be the same as what you would get. So there's no, if you were to create this state and measure x and p, there's nothing that violates any classical correlation. But it doesn't mean that everything about that what comes out of this two-mode squeeze state is classical. Because if I count photons, that's a non-Gaussian measurement. And that can have a complete, something that can't be explained in terms of classical statistics and violate and be a resource. It's very complicated and confusing. Right. So, how does one make this in practice? Actually, interestingly, one typically does not make this kind of two-mode squeeze state because it requires you to simultaneously be resonant for the two different modes. And it's easier in an optical parametric oscillator to have just one mode. But as we discussed, if I put squeeze states on a beam splitter, I can entangle them. So putting single mode squeeze vacuum into two ports of an interferometer, what comes out is something which is two-mode squeezed. That's to say the two modes, this mode and this mode, are entangled with one another. And that's how it's done. So it's really, I think it's quite amazing, quite interesting that this how much richness there is in this nonlinear optical process, and the different ways we can analyze the kinds of degrees of freedom, whether we're talking about properties of the particles, where they are, when they arrive, their spin, as well as if we think about these collective properties in terms of the modes and their quadratures, the continuous variables, which are generally superpositions of different numbers of particles, how they're correlated, and then how we might use those correlations for various kinds of information processing tasks. Does anyone have any questions?
Well, I
So
guess,
just
oh, I'm sorry, go ahead.
go ahead, go ahead.
Well, maybe we can talk about this later. So you send a squeezed photon through a beam splitter.
Yep.
It doesn't generate two photons. It just statistically goes through one or the other. So what's entangled?
Well, it's not that I send one photon. It's that I have these photons here. I'm not gonna, let's say that I send two squeeze vacuums, one into this port, one into this port, and the other into that port. Okay.
Oh, okay.
Because I don't know from once I see the photons coming out the output ports, there are indistinguishable processes about whether the photons came from here or here.
Yeah, okay.
And because of the statistics, they are now correlated.
Yeah.
And because of those correlations, it becomes entangled.
Yeah. Okay.
I'm not going to create more than one photon at the beam splitter. I needed to have created that squeeze vacuum through a parametric oscillator before. Let me show you a schematic of, so this is something that's in the notes. I'm not going to talk about it right now. Let's see. So this is from a famous experiment that was done in Jeff Kimball's lab in 1998, where they teleported the state of a mode from one side of the room to the other using the protocol of quantum teleportation. We don't really I don't have time, unfortunately.
That's fine. Yeah.
But
Thank you. Yeah.
but I just but I just mentioned that the way they did that is they have an optical parametric oscillator, and then they create they have two ways the light can come out of that oscillator. They put it onto a beam splitter, and that created entanglement. One side went to Alice, and the other side went to Bob.
Okay. Yeah.
Alice is really Lee. That's my student Lee. That's my student Bob, and that's my student Charlie. But we changed Lee's name to Alice for the purposes of this. And that's the way in which one of the ways you can create a two-mode entangled state is that if you have squeezing on a beam splitter, the output state becomes correlated and squeezed. I mean, and it becomes an entangled.
Entanglement. Yeah. Okay.
Mohsen, you had a question?
So, Ivan, you were saying that squeeze state is Gaussian, but when you do like number measurements on it, they are entangled. So it's not really like.
Well, I wouldn't say that they're not entangled. They're entangled with the Gaussian
Oh, they
state,
are
but they don't
entangled. They're entangled.
correlate local realism.
Yeah.
They're so right. So the two modes are entangled The EPR state is an entangled state, but it doesn't violate local realism. If I were to measure quadratures, X and P, because the Wigner function gives me a way of assigning a local hidden variable realistically. I can imagine a random number generator that samples from the distribution of Gaussians and distributes to the two parties oscillators that have this distribution of X and P. And then the parties can measure that, and they'll see measurement outcomes that are correlated, very strongly correlated. But strong correlation doesn't give me a violation of local realism unless there doesn't exist a probability distribution that's everywhere positive.
Interesting.
Yeah. But the distributions of correlated photon counts or polarizations would violate a Bell's inequality.
Interesting.
Yeah. So not every measurement that you do will necessarily not, some of them have a perfectly classical statistical correlation, but not everything.
Very interesting.
Yeah.
Thanks.
All right. Any other questions? All right. Well, I'm sorry to make you relive the trauma of Zoom remote lectures. We'll come back in person, and I'll see you after spring break. There will be, a new homework assignment coming. It will be a lighter assignment, but, you might want to take a peek at it while you're relaxing on the beach. All right, everybody. Take it easy.